So this is the lab for the capacitance, and I'm scrolling through the motivation and objectives and theory part. So what you have to figure out is actually the capacitance of a capacitor, which stores energy and charge and is an integral part of any kind of circuit that we're using for any kind of electronics. You have lots and lots of capacitors in there, and use them for other purposes too. So it's very important. There is no really there isn't an easy way of figuring out what the capacitance is. So I'm using this particular experiment to measure that. There are the parts, of course, that I'm going to use from the snap circuit, and this is the typical setup here, except I have two capacitors here. This is the resistor. It's a large resistor, 33,000 ohms is what I'm using. And in order for the time to be long enough that we can actually take measurements, and then these are actually two capacitors in series, but I'm going to start out with just one capacitor at a time, and then I'm going to do the other capacitor, and then I'm going to go to the parallel circuit, which is, by the way, down here. You can see that they're in parallel here, and then finally I'm actually going to go to the series one. The voltmeter here is going to measure how much voltage I have on the capacitor, and then the reason why the cell phone is over here is because I'm using it as a timer. Or you could use it as a timer. Let's see, scrolling down here. Okay, this is my example. It's posted on Desmos, and I will show you that analysis later. And what happens in the experiment is that I'm going to measure these 15 data points from time 10 to 150 seconds. I'm skipping 0. There's really no need to have that extra data point, and it really doesn't matter if I turn on the switch at the same time that I start the timer. It really doesn't matter. So 10, 20, 30 is where I'm going to measure. And then I measure the charging voltage, and you can see that obviously it goes up, but it's going to go up slower and slower. You can see at the beginning these are large increments, at the end they're small increments, and you can see it on the curve. This is the charging curve here, that it goes further up and up and eventually tops out. This is kind of like 1 minus the exponential. It's kind of like really written very small right here, but I show that later in Desmos in more detail. This one here is the discharging curve. So after it's charged, I just leave it like that, unhook the battery, and then discharge it, and you can see that the voltage is going down, but then again you have large increments by which it goes down at the end. It goes down by very small increments, and you can see the curve here, and that's a typical exponential curve, decay curve, and again you can see that very tiny here, and again I will show that equation in more detail later. This would be the analysis. So here I used, in my example, I used a 99,000 ohm resistor. In the circuit later on it will be 33,000 ohms. I also will use different capacitors. Here I used 3 capacitors in parallel. I'm not going to do that in the real experiment. It's just my example here. And I have 470, 220, 100. And what I expect is if I add them up, notice that these are capacitors in parallel. And I said add them up, right? That's different from resistors in parallel, where they actually would be adding the reciprocals, but here apparently it's simply add them up to 790. And then when I measured it with the charging, when I analyzed these curves here for the charging and discharging, this is what I got. And you can see that the 800 matches the 790 nicely, and that the 800 over here also matches it nicely, and that comes from the analysis. So that justifies to add them up when they're in parallel. So I think you can guess what's going to happen when I put capacitors in series. All right, there's two more pages, I'm sorry. This is actually then the analysis. So besides the Desmos that we have to use to actually do the exponential curves with us, we also have to use these equations over here. Actually, it's really only one equation, figuring that out. And with that, we're going to fill out this table here. And then there's one more page after that, so please fill out this information here based on the data. There will be no conclusion, by the way. And then there's a few more things here, but you're skipping it all. So you look at my example in table 0 up there. You look at the actual table 1, the data that you get from my video experiment. But these are table 2, table 3. You're gonna skip, and there's a long addendum, and you skip that as well. All right, let's go ahead and do the experiment. So this is going to be the experimental setup for the capacitor lab. Need a battery, the capacitor, of course. I think I'm going to put that here. For some odd reason I have very few wires. This is the resistor. I need to use the largest possible resistor, the 33,000. Let's actually measure that. That is true, because it allows me for the capacitor to be charged at a reasonable time that I can actually take measurements, and sure enough it's 33,000, because it's 33 kilo ohms, 33,000 ohms. So yeah, that the capacitor can actually be charged in slow enough time that I can actually take measurements. Put a switch there and then connect. I think I already said for some odd reason I have very few wires available. Ooh, and then my switch is already on. Better not do that. There we go. I just turn it off. Alright, and then the voltage is going to be measured here. Of course I have to turn it to voltage. If it shows a negative, let's just see. Yeah, it shows a negative. All I have to do is turn it around. I just turn a switch on so the capacitor is actually charging. If I want to discharge it quickly, that's all I need to do. Just a jumper wire without the large resistor. And there you go. Okay, so that's the basic setup in order to charge the capacitor, and then I will measure every 10 seconds. So I'm just going to show you here. This is not, oh yeah, and then I turn the switch on, turn the timer on. If I don't turn it on at exactly 0, that doesn't matter. That's why you don't have it on the data sheet. But 10 seconds matters, and take a measurement right now. Except we're not, this is just a trial run. I just want to show you how this particular experiment works, and then I would take a measurement right now, and so on. So again, this is just a setup. So I'm going to stop this one here. I'm going to stop the watch as well, reset it, and this is how the discharge would work. So I disconnect the battery and make a closed circuit again, and now I start the switch and the timer, and we can see that it's discharging as the voltage is going down. And again, I would measure every 10 seconds, such as right now, and then so on, 20, 30 seconds, all the way up to 150 seconds each time. Alright, that was the setup, and next I'm going to do is the actual measurements for the first resistor charging and discharging. Alright, so it says 0.01. Oh well, I'm just going to get rid of that quickly. There we go. Alright, start the switch and start the timer and measure every 10 seconds. So while I was doing this here between midnight and 2 o'clock, I had a few mishaps, and measure right now. And the major mishap was that as the camera filmed, I noticed that the picture in the viewfinder was quite large, and measure right now. And then when it actually filmed, it cut the top part off, so it actually never measured this number up here right now. So I have to redo my first couple of measurements. That's when I noticed it, and I guess I wasted 15 minutes. I don't think that's too big of a deal. Right now, measure, and so on. Yeah, and for some odd reason, I have very few wires available, but I'll make do right now. And let's see, what else did happen earlier. Somehow, yeah, something with the setup at some point, so I had to measure here a moment ago after 60 seconds, obviously, and would measure right now at 70 seconds, and so on. Yeah, oh yeah, one thing that happened, again, I deleted these videos because this was always cut off, so at some point I accidentally discharged it while I was actually going to do the discharging part with this wire here. So when I'm done with this, I'm not going to use this because I need to measure while it's discharging. So apparently we have another 40 seconds here going, and I might just do the whole shebang here for the first capacitor. I hope I said capacitor all this time. This is the resistor, which again is just very large, 33,000, to give it a reasonable time that we can actually measure something, but it's actually about the capacitor measuring the capacitance with this particular experiment. And of course we're collecting all these data and then put them into an analysis such as Excel or Desmos, and that will actually analyze the data for us. And that would be the last measurement right now. Okay, I can leave it a little bit on for a little longer time, doesn't really matter, but at this point here I'm gonna stop it, reset it, turn the switch off, unhook the battery, and then reconnect, make a closed circuit, and then start the switch and start the timer. And now it's discharging. And again, take a measurement every 10 seconds. And this time everything shows right now. Yeah, everything shows nicely in my viewfinder and on the camera. And take a measurement right now. Alright, so I'm not going to talk the rest of the time here. Just going to read my book, Frank Herbert, Der Wüstenplanet, in German. Alright, almost done here. And take the last measurement right now. There you go. Okay, and I'm gonna stop the switch, stop this one, there we go, and discharge the first capacitor. Then I'm gonna do the analysis of these data next as an example analysis, and then I will measure the second capacitor, and after that capacitors in parallel and then capacitors in series. So here's the analysis of these data in Desmos. These are actually the example data, and I want to show the most important thing that you come across, which is the share graph here. You click on it and notice the link it says here, that's what you need. In fact, you should save that link once in a while, and every time you do something, notice the 7 pick here. I'm going to click out of it. I do something, just shift this around here, and notice that it totally changed. So whenever you do something here in Desmos, it actually changes it. So make sure to save it on and off just so that you don't lose previous work if your something happens with your computer or something. Anyway, this is the example here that you already saw in the lab manual. I'm going to turn these off. It's very easy to do without taking them out. I don't want to take them out, so I just turn off the data points, and I'm going to turn these lines off, these exponentials. And now here I'm going to fill in the capacitors, the charging and the discharging for the first capacitor. But in order to do that, I actually have to watch my own video, listen to my own voice, which is, as you know, never really comfortable. You know, we don't like to listen to our own voice. So I'm going to put these in. I'm going to actually pause the video, so when I come back in a few seconds in the video here, it actually took me a couple of minutes to review my own data. So see you in a moment. And I'm back, and that only took me a few minutes to put in these values here. I didn't put all the values in here because I figured you can do the rest then. Okay, notice that these are not highlighted, hence they don't graph. So if they're not if they don't graph, then just click on them. And again, there's this little plus sign here next to the table, and then it kind of puts it nicely into the screen. Apparently the curves are not highlighted either, so I will do that. There they are. And again, if I didn't turn off the example, then you would get all these other data here. So I recommend that you actually only work on one at a time. So I'm going to turn off my example, and we'll just look at the data that I got for this first capacitor for the video experiment that I made for you. So again, I only filled in the first 8 data points for charging and discharging, and we can see that it nicely goes up, and it starts to top out, and the discharging data go nicely down. Of course, they do bottom out. The equations are here, a simple exponential for the discharging one, and then 1 minus the exponential for the charging one. Again, the regressions are 0.999 or 1.000, which means that are near perfect. I don't need the total voltages here. What I do need is the time constant. So this one is 46 seconds and 58 seconds. And I'll use these to plug them in here. So what did I just say? I have to go back. 46 and 58. Ooh, that's widely different. Okay, so they go in here, 46 and 58. And I will change that to a different font so it looks like handwriting. The resistance is 33,000. The expected capacitance, I mentioned that in the video, is actually 1500. Now this value here, that's kind of like the expected time constant. I would have to multiply these two numbers with each other, so I'll do that. 33,000 times 1500 and divide by 1 million. So I come up with 49.5 or 50. So now I'm going to go backwards. So I'm going to do 46, right here, the 46 divided by 33,000. Again, that's, let's see, I can almost see that equation. It's kind of here, a little bit hidden. There it is. So time constant divided by resistance. And I'm going to spare us to multiply with 1 million. I think we can see that when we do that, shift the decimal point 6 times, I come up with 1,393, which I will round to 1,400. And then for the discharging one, it's going to be 58 divided by 33,000. And again, times 1 million comes out to 1757, which I round to 1800. And we can see that they're not exactly on, but these are typical results. We're off by a neighborhood of like 10% or so from the capacitance value. Actually, if you took an average of these two here, then you actually are really close to 1500. Also notice that I only took a few data. I ask you to put in the remaining data for this one here as well. And then you do the same analysis for the second capacitor with Desmos, and always remember to, with that share link, that you keep copying that. And then for the parallel capacitors, and then for the series capacitors, and then fill out the page on the next page. And remember that there will be no conclusion, just answer these questions. Now, when you're done with this one here for the first capacitor, scroll down and you will see the second capacitor, and then the parallel capacitors, and then finally the series capacitors. And what I'm going to do now is I'm actually going to set it to the default. So I'm going to turn the first capacitor off. I'm not going to take the data out. There we go. And I will put the example back in. There we go. And I guess hit that little plus sign there. There we go. And yeah, then you can go from there. So I recommend you actually de-highlight these here, or whatever the word is, and then start working on the first capacitor and then the second capacitor and so on. So here's the analysis. In Desmos, notice this is my account. You're actually going to use this particular one here, but don't worry, as you're not saving it to my account, you're not messing anything up there. Perhaps the most important one is right here. This is where it says share graph, and you get this one here. When you're done, share this link. So you just click it and you copy it, Control-C, and then you paste it into the lab report, and then I have it. And notice that this link here will be unique. You see the B5SQ here at the end? Let me just get out of this here and let me just do something. For example, just shift this one around here. And let's see if I click to share. Notice totally different links. So whenever you do something, it will actually change. I would recommend that once in a while you kind of like take that particular link and just paste it somewhere in there so you're not losing the work that you already did. All right, so let me show you. Oops. Oh, great. How did I do that? Oh, I opened a new window. All right. So here are my example data that you had already seen in the lab manual. So increasing charging and then topping out, that's this curve here, and then decreasing during this charging, and then it bottoms out here, so that's exponential curve. And not only are the data on here, but you also see the regression curves, the exponentials that are apparently really close to the data, which means I took really good data, and turns out that if you were to do the experiment, all students always take very good data, because the only error source that you have is the multimeter itself measuring the voltage, and of course the timer here, and it really doesn't matter if you're off by a few tenths of a second. Anyway, this one looks a little bit off screen here, so I'm going to scroll down a little bit, and there's a little plus sign right here on the table, and now it puts it nicely back into the window so we can see it. So I got the data here. You can see them over here. By the way, if I click these here, just click, and the data are gone, right? Okay, right beneath it, I have these equations. This one here is a typical exponential with the negative, meaning that it decays, so it goes down and down and down. That's the discharging one. Again, when I click this one here, there, it's gone, right? And then this one here is 1 minus the exponential, so that's kind of like mirrored. I think you can see that the charging one is a mirror image of the discharging one, and it goes to zero, goes through zero, because it apparently starts at 0 voltage when it's being charged. And so both of these describe these data. All right, so let's look at the numbers over here. There is an R² value, which means that's how good the regression is. Notice I have a 0.9999, and that means my regression is virtually perfect. Same thing over here. There's a second number here, the voltage, that's kind of like the top voltage, 2.74, and the other one is 2.30. That's where it tops out. I actually don't need that. The only number that I need is this tau here, which is the time constant. So this one here says 74.5. I will use that. And this one here says 78.1, and I also will use that. And you see it in the equation. It's right here. The tau right here and the tau right there. So I will go over to my lab manual and use these numbers. And so apparently the 74.5 rounds to 75, and the 78 point something, I think it was 78.1, that should round to 78, not 79. There we go. All right, and then using these time constants, I will compute the capacitance, the total capacitance. So I'm going to do 75 divided by the resistance. The equation is right here. Capacitance equals time constant divided by resistance. In this case, I used 99,000. So there we go. Come up with this number here. This is in farad. Notice that it's a small number. In order to get into microfarad, well, micro is 1 millionth, so I'm going to multiply with 1 million. There we go. And I come up with 757 microfarad. I want to use 2 sig fig, so 760. I'm not sure exactly why I previously wrote here 800 as if it was just 1 sig fig. It ought to be 760. And that's based on that my times here are pretty much 2 significant figures, right? These are not a rounded 90. I really tried for 90 seconds, not 89. So I would actually have 2 sig fig. All right, the other one is, I'm going to do 78 divided by that. There we go. And again, multiply by 1 million. Keep hitting the second entry button. That's really nice on a TI calculator. And I come up with 790 microfarad. And notice my results as compared to the expected one is actually really right on and justifies that capacitors in parallel add up their capacitances, which is unlike resistors, which would add their resistances if they were in series. So capacitors in parallel do the same thing as resistors in series. Okay, so second time as a charm, it actually worked. I did film it correctly. So now I'm going to switch to the second capacitor. So the first one is supposed to be 1500 microfarad. Of course, that's what the experiment is about to determine that. And the second one is supposed to be 2200 microfarad. So I'm going to put that one in and hook it up again. Just going to see. I want you to ignore the negative there. Oh, connect. And so I will switch these around. So I'm not measuring just yet. I just want to switch it in such a way that we can ignore the negative. All right, ready to measure. And switch on. Timer starts. Timer starts. There you go. And again, measure every 10 seconds, such as right now. And I will actually read my book, Der Wüstenplanet. Wo ist Alia? Fragte sie. Sie ist draußen, sagte Paul, und sie tut das, was jedes echte Fremdkind in solchen Zeiten tun sollte. Sie tötet verwundete Gegner und markiert ihre Körper für die Teams, die deren Wasser einsammeln. Paul,
Du verstehst hoffentlich, dass sie dies lediglich aus Mitleid tut, fuhr Paul fort. Es ist nicht seltsam, wie oft wir vergessen, dass Mitleid und Grausamkeit einander so ähnlich sind. Jessica starrte ihren Sohn an. Die unerwartete Veränderung schockierte sie. Ist der Tod seines Kindes daran schuld? Fragte sie sich. Dann sagte sie, die Menschen erzählen sich seltsame Geschichten über dich, Paul. Sie behaupten, du hättest alle Kräfte der Legende, dass man nichts von dir verbergen könne, dass du alles siehst, was anderen verborgen bleibt. Sollte einem Bene Gesserit solche Fragen stellen, erwiderte Paul. An allem, was du bist, bin ich nicht unschuldig, sagte Jessica. Du solltest also nicht. Wie würde es dir gefallen, Milliarden und Abermilliarden von Leben zu leben? Entgegnete Paul. Sie würden eine ungeheure Sammlung von Legenden für dich mitbringen. Denk nur an die unschätzbaren Erfahrungen und die Weisheit, die sie mit sich bringen würden. Aber Weisheit kühlt die Liebe ab, nicht wahr? Und umgibt jedweden Hass mit einem neuen Kleid. Wie kann man sagen, was Unbarmherzigkeit ist, ehe man nicht alle Tiefen der Grausamkeit und des Mitleids ausgelotet hat? Du solltest mich fürchten, Mutter, denn ich bin der Quieser Zaderach. Jessica schluckte. Ihre Kehle war wie ausgedörrt. Plötzlich sagte sie, es gab einmal eine Zeit, da hast du mich wegen dieser Tatsache abgelehnt. Paul erwiderte Kopfschütteln. Ich bin jetzt nicht mehr in der Lage, irgendetwas abzulehnen. Er sah ihr in die Augen. Der Imperator und seine Leute werden bald kommen. Man wird sie jeden Moment ankündigen. Bleib bei mir, ich möchte sie im klaren Licht sehen. Meine zukünftige Braut wird ebenfalls unter ihnen sein. And take the last measurement now. All right, getting ready to discharge this capacitor. Gonna turn the switch off now. Stop the timer, reset the timer. At least I'm trying. Oh, what did I do? There we go. All right. Okay. Disconnect the battery. Close circuit again for discharging, and turn the switch on and start the timer. Again, it's never crucial that the two are at the same start at the same time because you're not measuring the 0 point. All right, and take the last measurement right now, or 1 second before that. All right, got the second capacitor done. Alright, so now I'm going to do two capacitors in parallel. Of course, the capacitor, or in this case the plural, always have to be in series with the resistor. But now I'm going to put the two capacitors in parallel. That's actually quite easy to do. So there we go. Okay, turn this one back on. Okay, here it actually doesn't matter if I'm going to measure here or here. Apparently they're still a little bit charged, or this way, as long as I measure across these two here, because everything is connected on each side here. So let's see. Actually, I'm going to switch them because I didn't want to have that negative, right? So there we go. Okay, reconnect the battery because I'm going to do the charging. And actually, I'm just going to see what happens when I do this. Okay, alright, okay. So I discharge them here very quickly. There we go. Turn the switch on, timer, and we're in business. Charging two capacitors in parallel. Measure right now, like 2 seconds ago. By the way, I think me reading once in German, I think, was enough. Alright, and take the last measurement now. You see that apparently with two capacitors, it really takes a long time to charge them. Alright, I'm going to stop this one, stop that one. Don't discharge it. I need this. Okay, unhook the battery. And there we go. Reset the timer. At least I try. There we go. And start discharging. And the timer. At least I try. There we go. Okay, so here we have a couple of capacitors in parallel. So take a measurement 3 seconds ago. And take a measurement right now. So two capacitors in parallel. In a previous lab experiment, we had resistors in parallel and resistors in series. And as you learned, resistors in series add their resistances, while resistors in parallel at the reciprocals of their resistances, and then you have to invert it one more time. So here we have capacitors in parallel, and soon we're going to have capacitors in series, and they ought to do also something with adding capacitances and adding reciprocals of capacitances, and you will see how that turns out for capacitances in parallel, respectively, series. Alright, take the last measurement for discharging these two capacitors in parallel right now. I guess I always let it run a little bit longer. Alright. Okay. And finally, two capacitors in series. I'm going to reconnect the battery, make sure that the switch is off, and might as well discharge them right here. There we go. Okay, I have to do a little bit more work on this one here. The other one was really easy to set up. This one isn't so tough either. But here we go. This is a little tough of a board here. There we go. Got all connected, so they're all in series with each other, including the resistor, of course. Alright, so I can hook up the voltmeter. In this case, I have no choice. I cannot measure here. I cannot measure here. In fact, if I turn it on, there we go. Now I'm measuring only one capacitor. Here I'm measuring only one capacitor. And here actually I'm measuring nothing because I only have a wire in between. So it has to be over here. And again, I'm going to turn this one off and discharge the two capacitors in series. And you already noticed that this goes very fast. They're charging up very fast. So I'm only going to do 100 seconds instead of the 150 that I used to. And why is it? Discharge again. There you go. All right. So turn the switch on, turn the timer on, and start measuring very soon here at 10 seconds. As you can see, it goes up quite fast. Measure right now. Alright, and take the last measurement right now, because that's when the 100 seconds are done, and notice it actually barely at all goes up anymore. So I'm going to turn this one off, unhook the battery, and get a closed circuit again. Reset the timer. There we go. And start discharging. Again, it goes down quite rapidly at first. Right now. Alright, and take the very last measurement right now. Okay, again, I always let it run a little bit longer, and we're finally done with this experiment. It took me in the neighborhood of close to 3 hours to film all this, and I think the total footage is in the neighborhood of 25-30 minutes or so. Alright, and then I still have to edit it actually. So, there we go.